Focus on Physics, proudly brought to you by Gauteng Department of Education and Saibono Discovery Center. Right, now we shall be also interactive on our WhatsApp platform. The WhatsApp number is 064-748-8913. Just to repeat the number once again, it's 084-748-8913. So the purpose of the chat platform is for you to actually get interactive with us, share your comments, your questions, any clarity with regards to paper one. So we shall only focus our attention on the paper one as it is in the eve of our prelim exam tomorrow. Right. Now, without any waste of time, we shall dive straight into it. Right. Let's look at the structure of the paper one once again, just to remind ourselves, because this is exactly how it will look like, in the prelim exam leading to the final senior certificate exam. Right. So it's still out of 150 marks with a duration of 3 hours. Now, in the 3 hours, you need to manage the time very, very carefully, because time management is a very, very important part of the exam. Now, for section A, we've got 20 multiple choice questions that are of different levels and different types of demand. So in some of the questions for multiple choice, you'd actually need to apply yourself a little bit more. So already that would have some implications in terms of how you actually manage the time. And then the long section, which is section B, a total of 130 marks, which covers all the topics in paper one. Right. Now, in as far as the breakdown, the mechanics, which is by far, the bigger portion of our, our first paper, that's 63 marks. So that's your vertical projectile motion, that's your Newton's laws, that's your work, energy, and power, that's your linear momentum and impulse. So if you put all those topics together, they will give you a total of 63 marks. That is inclusive, of the multiple choice as well. Right. And then we've got sound, wave, and light. Our special focus on sound, wave, and light is precisely on the Doppler phenomenon. Okay, that's the part that is quite relevant. So that would carry a total of, give or take, 17 marks. And then electricity and magnetism. Right. Now, just to break down the part on electricity and magnetism, that's your electrostatics as you know it from grade 10 and 11. That will be your circuits. That will be also your electrodynamics. So those are the 3 subsections in those 55 marks. And then last but not least, the 15 marks on matter and materials, which is an overlap in as far as waves are concerned, because we talk of electromagnetic radiation and the photoelectric effect, which is actually the core focus. So all in all, this you shall be given 3 hours to actually complete that examination. Right. Okay. Now let's look at something very, very critical. Where exactly do we get the easy marks? These are what you'd want to think of as our low-hanging fruits. So the first one, it has to do with definitions. There is no way that you are going to go into the exam without the understanding of your definitions. Why? Because the minimum strategy that we've been using to say each and every one of us must be able to get that 45 out of 150, which if you do your calculations, that gives you a minimum of 30%, right? Just on the definitions. So one cannot overemphasize, the importance of definitions. Now, what's our point of reference? Once again, we've been saying this from the beginning of the year. As far as the definition, what is acceptable according to the examiner is what is in the examination guideline, right? So look at the keywords for each definition. Make sure that you use those keywords in the correct context. What exactly do we mean by making use of the keywords in the correct context? It's not enough to have the keywords in a definition. However, beyond that, when I read that definition, it must convey the correct scientific facts. That's what we mean when we say the keywords must be used in the correct context, right? And furthermore, in every long section in question B, there is also a question on definition. So you from question 2 until question 10, they'll be defined something, state, look out for those keywords or those action words that require you to actually define in many ways. We'll look at practical examples of such and see maybe a better way of trying to say, okay, take note of this. If it's a definition, it may be examined in this way or in that fashion. So we shall, have time in our session today just to look into those possibilities. Right. And then the formula sheet. Let's agree. Physics is concept. Right. So there is no concept without a mathematical equation. Right. Whether you start from the Newton's laws until you talk about energy of a photon, we are talking equations, we are talking formulae. The one that is always attached for your use at the end of the question paper. So as a result of that, always make sure that you are familiar with your formula sheet, because the concepts themselves, they are expressed mathematically in those equations, in those formulae. All right. And then time management is something that's very, very key. All right. In the 3 hours, for you to better manage the time, there is no rule that says you need to start with question 1 and end with question 10, if whatever the case may be, right? So during the 10 minutes reading time, you're not writing anything. You're merely going through the scenarios in different questions that you are supposed to answer. Remember, we don't choose, we answer all questions. So in that 10 minutes reading time, make sure that you identify the questions that you are most likely to get a lot of marks. Start with those questions. What's the benefit of that? The moment you start with the questions that you can get the most, it means you spend less time, trying to finish that question which you can get a lot of marks. Then it means, by logic, you have got a lot of time to answer those questions that will demand more from you, that would actually struggle. Let's hope you do not struggle tomorrow, right? And you can start with question 10. You can start, but make sure that you number the questions as they are numbered in the question. So follow the instructions. Order is not of importance, but you can't mix question 5 with question 7, right? So to make it easier for you, start with the question that you get the most marks so that you better manage your time, right? And then speaking of defining or remembering skills, which is entirely based on definitions, remember, it's all or nothing. So if a definition is 2 marks, you need to know the definition. It's either you know it or you don't, and then there's nothing in between, right? And then the other one that's also a thorny point is the multiple choice. Multiple choice is question 1, 20 marks. There is no way that you're going to use 5 minutes left to answer 20 marks worth of questions, yet you'd have peggled on a question that carries 10 marks. So it means with the multiple choice, you must allocate a decent amount of time. And by all means, grade 12, do not leave the multiple choice question unanswered. Our last resort is to take a guess, but we'll guide the process of how you do that if all else fails at the end, right? Okay, we have spoken about the keywords in the definition. There's nothing that we have left in as far as that, but we shall look at practical examples of such. Okay, right. Now, remember, Metric is a 3-year course which stretches from grade 10 to grade 12. As we're sitting now getting ready for the preparatory exam, a lot of the exam is going to demand a lot of work that we've done, in both grade 10 and 11, because this is a 3-year course. Now we are at the exit of our 3 years of, our Metric course. So let's remind ourselves again, what are those things that are very, very critical in as far as grade 10 is concerned, right? First one of all is the principle of quantization of charge, right? And we've mentioned that for any principle, for any concept in physics, for any problem, there is always an equation that's involved. Now, in this case, you remember very well, it will be Q is equals to N multiplied by E, right? This says to us that every charge in the universe, is quantized in the sense that, every charge that exists is an integer multiple of the elementary charge. So the elementary charge is the charge of the electron, which is negative 1,6 times 10 exponent negative 19 coulombs, right? So if that's the charge of a single electron, it means for any charge that actually practically exists, it will be multiples of this charge. That's what the principle of quantization of charge says to us. And then we also talk about the law of conservation of charge. This is in your electrostatics. We are still in grade 10. It says Q net is equals to Q1 plus Q2. It could be any number of charges, right? And then if two charges are brought into contact and separated, they share charge, but ultimately during that physical process, the amount of charge remains constant. And then we therefore went on and says the new charge that each one of them has is equals to Q net divided by 2. So this is around the principle of conservation of charge. And then again, in grade 10, we looked at uniform acceleration and uniform velocity. Why is uniform acceleration important in motion in one dimension? Because in grade 10, we looked at motion of an object moving horizontally. So if we're saying that an object is experiencing a uniform acceleration, what exactly does it mean? It means that its velocity changes by the same amount for every second. And then where did this take us? It took us to exactly to G is equals to 9.8 meters per second squared downwards. Now, this is with respect to vertical projectile motion. So a lot of foundational knowledge that we did in grade 10 becomes very important in as far as VPM is concerned. That's why I'm zooming into uniform acceleration. And then we also looked at the principle of conservation of mechanical energy, which is exactly that equation, right? Now, to say when is mechanical energy of an object conserved, it should be in a closed system, right? Now, when exactly do we say, yes, indeed, mechanical energy has been conserved? When the total of the kinetic energy as well as the gravitational potential energy remain constant. So in grade 10, we confined our understanding on the principle of conservation of energy in the sense that it's a closed system, right? So mechanical energy of an object at two different points will be equal. That's what we meant when we said the energy is conserved, right? So that's grade 10. Now, grade 11, there are some aspects also that we looked at in grade 11, which has to do with the Newton's laws, okay? There's 4 of them, right? The first law, second law, third law, and obviously the law of universal gravitation. Go back to examination guideline, be able to recite each one of them word for word, be able to get those free marks of defining each of those. It can be a combination of any of them, or it can be one of them. But either way, you need to understand a scenario which is in which the first law is applicable, the second law, and so forth, right? And then grade 11, we looked further into Coulomb's law, right? And electric fields as well as electric fields at a point. All this is grade 11 work with a lot of marks in paper 1 of physics that you need to remind yourselves of. Go back and remind yourself what the Coulomb's law says, right? Understand, how we carry out calculations, simple routine calculations. You copy the formula, substitute correctly, do the necessary calculations. And I think by now you've realized something. For every concept that we talk about, we always refer to the formula sheet. So even in your attempt of the questions in the final exam, you need to draw your attention each time to the formula sheet. Very, very important. And also in grade 10 and 11, there was a very lengthy part that we did in as far as electric circuits, series circuits, as well as resistors that are connected in parallel. Right. So that's where everything started. So I'm trying to remind ourselves of some of the things that might have gone with the wind, but which are still remain critically important to us. Right. Okay, guys. Let's look into the big ideas in as far as the Newton's laws as our point of departure for now. Now, it says here, the Newton first law. What's so special about Newton's first law? If an object experiences a zero net force, does it mean there are no forces acting on it? Definitely not. It means the sum or the resultant of all those forces acting on that object, they give us a total of 0. So what would happen in terms of the state of motion of that object experiencing a zero net force? Two things may happen. It's either the object is stationary, or the object is at rest, or the object moves at a constant velocity. Right. Now, the key word or the conjunction is or. You can't be in motion and be at rest simultaneously or at the same time. What we're simply saying is that if there's a zero net force, the object maintains its position, it stays there. That's why the law will say the object will remain at rest. Or if it was already in motion and it experiences a zero net force, that object will maintain a constant velocity. Now, it takes us back again to the two forms of motion that I briefly referred to, uniform acceleration and uniform velocity. So in as far as the first law, the constant velocity that we're talking about here is definitely the uniform velocity. Okay. So what do we mean when we say the velocity is uniform? The velocity of the object doesn't change, which makes us say that the object experiences a zero acceleration, or the object is not accelerating. That's first law. So what is it that you look for a scenario that deals with the Newton's first law? You are looking for the keywords such as the object is at rest, the object is at equilibrium, the object is moving at constant velocity. And time and again, the examiner will write those keywords in bold capital letters. Pay attention to that. Right. And then as far as the Newton's second law, right? The difference between the first and the second is that in the first law, there's a zero net force acting on the object. Then we can therefore predict the state of motion. Object stays there, or the object maintains a uniform or a constant velocity. Then in the event that the net force acting on the object is non-zero, or it's not zero, what will happen to the object? The object must accelerate. Let's go back again, because when we say F net is equals to ma, we are saying that a net force, a constant net force, which is not equal to zero, when it acts on an object, the object moves with a constant acceleration. It means the velocity of that object changes by the same amount for every unit of time, which is equivalent to a second or 1 second. That's what we mean. So acceleration of an object is a consequence or a result of a non-zero net force acting on the object. Okay, let's remind ourselves once again. What does the law as we see it? If a net force acts on an object, the object accelerates. So the acceleration of the object is a result of this non-zero net force. I hope it makes sense. So you are looking for whether the object is accelerating or not. If it's accelerating, non-zero net force. Right. That's as far as the Newton's second law. However, there is also what we call the impulse momentum theorem. Right? What we have here is exactly what we call the impulse momentum theory. It says F net delta t is equals to delta p. Right. This is impulse. Impulse is the product of the net force and time. Right. That is equal to the change in momentum. So let's put this correctly. Impulse is not change in momentum. Impulse equals the change in momentum. Because essentially what happens is if a net force acts on an object for a period of time, the object's momentum changes. So it's a cause and effect. What caused the change in momentum of the object is a net force acting on that object for a period of time. I hope it makes sense. All right. So change in momentum equals impulse. However, rate of change of momentum, which is that, this one equals what? The net force. Right. So that's the Newton's second law. The net force acting on the object equals the rate of change of momentum. So if the examiner says state the Newton's law, you can state this version or the grade 11 one, which says if a net force acts on an object, blah, blah, blah. Right. So I think it makes sense. And then Newton's third law. Maybe we move into the Newton's third law. There's something that I need to clarify. What's common between the first and the second law is that we're talking about a single object. First law says an object will remain at rest. How many objects do we have? One. Second law says if a net force acts on an object, how many objects do we have? One. So for both the first and the second law, we're talking of a single object in space. Yet, if we talk of Newton's third law, we talk of body A and body B. That's where exactly the difference lies within these three laws. Now, there is a force exerted by body A on body B. and there's a force simultaneously exerted by body B on body A. Now, if you look at those two forces, those two vectors, they are equal in magnitude, yet they've got opposite directions. That's what is key. So this can be in the case of a collision. During a collision, as I'm clapping my hands like this, body A exerts a force on body B exerts a force on body A. That happens simultaneously or at the same time, right? So it's something that happens in collisions, even during explosions, right? For an explosion to occur, it means this is in the context of the principle of conservation of linear momentum. When an explosion takes place, body A exerts a force on body B, and simultaneously B exerts a force on body A, equal in magnitude in opposite directions, which is why they move apart, just like that, right? So that's Newton's third law. Take note, the minus in this context suggests the direction is different, right? So that's the big idea in as far as Newton's laws. We've already highlighted in terms of the problem-solving strategy that read the scenario carefully before you respond to the question. Look out for the keywords: rest, stationary, equilibrium. What do those words tell us? That there is a net force which is equals to 0. Sometimes the examiner would say the object moves at a constant speed in a straight line. That's uniform velocity. That's constant velocity, which is a result of a zero net force acting on the object. However, when it says it accelerates, it means F net is not equal to 0. Okay, it's either the object will move faster and faster or slower and slower. In both cases, the object is accelerating by the virtue of the fact that the velocity is changing, because in principle, acceleration is the rate of change of velocity, right? Okay, you do realize that each one of these laws has got a catch in terms of the keywords that you need to look out for to say, now in this scenario or in this problem statement, this is what is applicable. You need to understand those keywords that we've just discussed, right? There can never be Newton's laws without forces. Forces which are essentially vectors, all right? So in the application, which is your most likely your question 2, to say whichever Newton's laws will be applicable there, you need to identify the forces acting on the object, right? Free body diagram. There is no way you will exit the exam without drawing a free body diagram, okay? A free body diagram is a diagram that's free of the body. So in place of the body itself, we've got a dot. That's why we call it a free body diagram. I hope it makes sense. Now, pay attention to the mark allocation for a free body diagram. If the free body diagram says 5 marks, it loosely says to us there are 5 forces. If it's 3 marks, there are 3 forces, and so on. All right? Underline the keywords: rough surface, smooth surface. Okay, what are the implications of these keywords? They are saying to us that there is a kinetic frictional force, or we can ignore the kinetic frictional force if the surface is smooth or frictionless, right? And then pay careful attention to the mark allocation. If the calculation, say for argument's sake, is 3 marks, what that says to us is that you need to identify the formula, copy it as it is from the data sheet, substitute correctly. Just be careful in as far as the substitution is concerned. We only substitute SI units in our calculations. Make sure that the necessary conversions have been made. And then the last mark, make sure that you include the correct SI unit. Okay? Use a calculator, get the figure. Do not attempt to change the subject of the formula while you are at it, because it's not necessary. Copy the formula, substitute, get the answer, include the correct SI unit. If it's a vector, it's the SI unit and the direction. Unless the question says, calculate the magnitude of acceleration, right? Then you say, okay, 0.2 meters per second squared, whatever the case may be. But if it says the acceleration, the force, you must mention the magnitude and also include the direction. Also, that will be indicated in your mark allocation, right? Okay, so vectors in terms of direction, we've been through that. Then what happens if the calculation is 4 marks or beyond? What that simply says to us is that it's a multi-step problem. It means you have to do first part of the calculation, get that value or whatever quantity it is, use it again in another step to get the final answer. So those will be 4 marks and more in most cases. So pay attention again to the mark allocation. It's an indication of how much you have to do to get the full marks. Right. Okay. The data sheet, very, very important. Very, very important. Now, if, say, for argument's sake, we were talking about the impulse momentum theory. There it is. If a net force acts on an object for a period of time, it causes the object's momentum to change. Right? Also, take note, this is universal gravitation. Okay? There are 2 versions of it, whichever is fine. This talks about masses. It doesn't talk about charges. That's another, trap that more often learners, they fall into. So be mindful, if you talk universal gravitation, we are talking masses of objects, and this must be the distance between their centers, okay, unlike in the Coulomb's law. So make sure you can differentiate between those two. But for your, for your support, it's not a secret. The formula sheet is there for your use. Right. Okay, let's talk practical example of applications of Newton's laws. We've got a block of mass m, which is 8 kg, is connected by a light inextensible string. Let me explain what that means. The string is light. We're not going to take the mass of the string into account. The only masses that we shall consider is m1 and m2, full stop. And then if the string is inextensible, it means it doesn't stretch, meaning these 2 connected bodies, there's a constant tension force in that string, right? There's a constant tension force. That's what it means. It runs over a light frictionless, okay? There's no friction on the pulley, right? So it just moves over it. And then we're given the coefficient of kinetic friction. Now, as expected, 2.1, it's a definition. State Newton's second law of motion in words. In words, I must emphasize that you cannot go to the data sheet and copy the formula and say you've answered the question. It says explicitly in words. So what you need to do in this case is go back to the formula sheet. It will say F net is equals to MA. Get the 2 marks. Make sure that the mathematical relationship between acceleration and net force, between acceleration and mass are clearly captured. Then you can earn the 2 marks. Right? Now, what is of interest to me again is the free body diagram, because before any calculation that you do, you need to focus again on the free body diagram. Now, in this case, we need to indicate that, say for argument's sake, we're talking about M1 for argument's sake. Right? There's that force that is pulling M1 up the incline. That's tension. Let's call it tension 1 for argument's sake. Right? And then there's a force exerted by the surface on M1 perpendicular to the surface, which is the normal force. Right? And then we've got the weight of M1, which is mg, right? Okay, gm, mg is fine. Let's say fg. Some of you prefer to write w. But what's important, guys, about this force, we are not allowed to resolve. Ours is to identify the forces as they are. So we are not going to accept any components in place of the force of gravity. Right. So if this is a rough surface, because we are told there's kinetic frictional force there, it means if this block is moving up the incline, then the kinetic frictional force acts down the incline. Right? Now, how many marks is this? It's 4 marks. What does it tell us? There are 4 forces. 1 for every correct. Make sure the dot touches the tail. Make sure that there are correct labels. Make sure that the forces are in the right direction. So if it's 4, it's going to be 4 marks. So whatever follows from the free body diagram is based on the calculations, and the 2 must speak to each other. In other words, if we are to say, let's look at the forces that act on M2. We've got the tension force. Let's call it T2, right? Because so it's for M2. And then we've got the weight, okay, which is Fg, right? So these are the 2 forces. If we ignore air friction, we don't include the air friction. It means there are only 2 forces acting on that. So the issue of free body diagram is 3 marks as it should be, right? Okay. we're not going to go further than that. Right. And then multiple choice, we spoke about it. It's a 20-mark allocation. The time that you allocate for it to attempt those questions needs to be decent as well. For those of you who are potential distinction, you need to get a minimum of 16 in both paper 1 and paper 2 out of 20. You can do the calculations. It will make sense. You need to get a minimum of 16 out of 20. So by no means you shall leave the multiple choice unattempted. Okay. Now, while you answer the multiple choice questions, there is this approach of eliminating the distractors. That's the point of takeoff. So while you eliminate, think about why those options are incorrect, right? It's not just a random pick so that you move, but at the end of the day, it has to be informed by some thinking, right? And then pay careful attention to the keywords, especially those in capital letters, right? Which one of the following is not a vector? So not will be written in capital letters. Which one of the following is an example of inertia? Inertia will be written in capital letters and in bold. So pay attention to those. Okay. So upon completing these multiple choice questions, read the question, look at your answer, look at the option that you've selected. Ask yourself, have you answered the question? Okay. Because most of the time, while you are eliminating, you end up losing focus, and then that can cost you some valuable marks. Right. Now, here's a practical example of a multiple choice question, but this one is based on the law of universal gravitation. There are two objects, M1 and M2, right? You are allowed to even sketch them. There's M1, okay? There's M2 there, right? So the distance between their centers is D, right? That's the distance between their centers, okay? And then we're told that the force that M1 exists on M2 is F, right? Now, masses of both objects are doubled, right? And the distance between their centers halved. So two things have happened. We have doubled the masses and halved the distance. The question that we need to ask ourselves, from the law itself, we know that it says F is equals to G M1 M2 over D squared. Now, if we double both masses, what's going to happen to the force? The force will also increase, right? If we have both the distance between the centers, what must happen? It must also increase, right? So we know that the force is not going to decrease nor remain the same. It will actually increase. Then when we look at our options, all the four options say increase. 2F, it means doubled. 4F, 4 times as much, and so on. Right. So we know that this is F, right? Because left-hand side equals the right-hand side. Now we are saying that the new force is going to be G 2M1 2M2 divided by D over 2 squared. What have we done here? We have squared half the distance. You have not, instead of having the square of the distance, what we have done here, we have said distance is half, and then whatever that half distance is, we square it according to the law, right? Then this reduces to 4G M1 M2 over D squared over 4, right? This works out to 4G M1 M2 multiplied by 4 over D squared, right? Now I can see a 4 by 4 there, which gives me a 16 G M1 M2 over D squared. Now this is F, meaning therefore the correct answer there is 16 times as much, right? So you need also to use the very same approach if it were point charges in space as far as the Coulomb's law. So this was just an example on how to work around your multiple choice. And multiple choice, most of the times in physics, it actually checks your understanding more than your calculations. Instead of saying a mass of 2 kg, it will say a body of mass m. It means you need to know your stuff. Okay, and then moving further, VPM is another due to gravity is that this is a consequence per meter squared. So what that means is A is equals to change in velocity over change in time, which means the velocity changes by 9.8 meters per second for every 1 second, right? So meaning that if an object is launched upwards, is that object a projectile? Yes, because its initial velocity is not zero, right? But upon leaving your hand, that object experiences a constant acceleration. Why? Because beyond that, only the force of gravity acts on the object. So in principle, we are saying that a projectile undergoes free fall. However, not all objects are projectiles. What that simply means is that for an object to be a projectile, it has to be given a non-zero initial velocity, whether you throw it up or down, right? And then if it's in free fall, whether it's a projectile or not, there must be only one force acting on it, and that force is the force of gravity. Right. Let's look at a practical example, right? Now, if the question says air friction is ignored, this tells us that the object is in free fall. Okay, so it says the type of motion is free fall. Then the label there is force of gravity. This is a free body diagram of a free falling object. So if the object accelerates in the direction of Fg, according to Newton's second law, therefore it says to us that Fg is the only force, therefore acceleration due to gravity will always be downwards. That's why we're saying the object experiences a constant what? Acceleration. Equations of motion, they're not new to us. All the way back from grade 10, we've been doing these kinematics equations. From grade 10, we understand that these are vectors, especially velocity, initial, final, acceleration, change of position, which is your displacement. The only scalar in these equations of motion is time. And when you do calculations, the time that you get must always be positive, unless you mix things up. But remember, if it's a 3-mark question, always try to make sure that you get the formula, substitution, and answer. That's minimum, right? But first things first, you need to read the scenario carefully and understand what is happening, right? Highlight the keywords, underline the keywords, whichever way you choose to do it, right? And then thereafter, you must be able to draw a trajectory. A trajectory is the path that is followed by that object, okay? It's very important. Now, we've spoken about the vector quantities. If upwards is positive, downwards is negative. So if you say you throw something up at 10 meters per second upwards, its acceleration is negative 9.8 because acceleration is always downward. I hope it makes sense. Okay, so that's where you choose the direction and always refer to the data sheet. Right. Here is a practical example. Okay, there's a hard plastic toy. Okay, 0.6 meters high above the ground. Okay, there is the toy. Okay, is 0.6 vertical height, 0.6 meters. Okay. And then the building is 21 meters above the ground. Okay, the child throws a tennis ball. Okay, now is this the child throws a tennis ball vertically upwards? Is the tennis ball a projectile? Yes. Why? Because it's given an initial velocity. So instead of saying define a projectile, the examiner may ask and say, is the tennis ball a projectile? Then you say yes, it is a projectile because it's given an initial velocity. Is it in free fall? Is this type of motion free fall? Yes, because we ignore air friction, meaning the only force acting on that object is the force of gravity. I hope it makes sense. Now we are told it's prescribed now. Upwards is positive. It's even written in capital letters, right? We shall take upwards is positive. The mass of the ball is also given. Now, is the tennis ball, while moving downwards towards the car, in free fall? It's a yes or no. And then after that, you must justify or give a reason. Now, as the tennis ball moves from that edge of the roof to point X and all the way downwards, okay, until it hits the toy car, is it in free fall? Yes, because for all the time of its motion, the only force acting on it is the force of gravity, right? So this 3.1, in other words, is a definition, but it has been asked in a different way, right? And then calculate the magnitude of the velocity of the tennis ball that it was thrown, right? Okay, 3 marks. Now, what does this 3 marks tell us? It's formula, substitution, answer. So in the data sheet, it's written kinematics or mechanics. Those are the equations that you use, right? Now, you also make sure that you read the question and consider motion between any 2 points. There must be an initial position and a final position. Velocity at the initial position is initial velocity. Velocity at the final position, it could be a point X at the highest position. That's your final velocity, where the object stops. So the long and short of it is try to make sure that you actually, consider motion between any 2 points and stick to your direction, right? That was just an example on vertical projectile motion. And then another quick one is linear momentum and impulse. I've touched briefly on this. If the examiner says define momentum of an object, in the data sheet it's written P is equals to mv, right? Now, momentum is the product of mass and velocity of an object. That's 2 marks. And remember, this momentum is small letter p, okay? Because the capital letter P represents power. It's a different thing. It could be in mechanics or in the context of circuits, right? Also remember that, okay? Then we've spoken about the impulse momentum theorem. F net is equals to delta P over delta T. Now, this is self-explanatory. The net force acting on an object is equal to the rate of change of the object. Where did we get this? From the data sheet, right? Impulse, they've spoken about the impulse. F net delta T is equals to delta P. Okay. Impulse equals change in momentum. However, impulse is the product of net force and time. Also, this, you find it in terms of the Newton's second law. And then we've got the principle. Wherever we apply the principle of conservation of linear momentum, we must remember that the total initial momentum before collision or explosion equals the total final momentum after collision or explosion. And then when it comes to this one, these are 3 marks. To determine whether the collision is elastic or inelastic, make sure that you calculate total kinetic energy before, that's total EK initial, and then separately you calculate total EK final, right? And then make a comparison. If the total kinetic energy remains constant, it means the collision is elastic, and if not, then the collision is inelastic. And then sometimes the examiner may go further and say, what happened to the kinetic energy? Remember, during collisions, there's sound, there's heat and whatnot. So energy cannot be created or destroyed. It's converted or transformed into other forms. So you also need to capture that, right? So that's the long and short of the scope of what you call the linear momentum and impulse, right? So I've also alluded to the fact that collisions and explosions are the context in which we talk about linear momentum and impulse. So wherever there's a collision, there's Newton's third law, right? Force by A on B simultaneously, we talk about force on B on A, right? And then the change in momentum. But then for us, maybe to put this into context, I want us to use a scenario. But at this point in time, I would request that maybe we take a 5 minutes breather, and then when we come back, we look at that particular scenario. See you shortly.
You have been given power to decide whether you want good results in your life, in your schoolwork, or you want bad results. As Tony Robbins said, it is in the moment of your decision that your destiny is shaped. And your destiny is shaped right now. with the decisions that you are currently making in your schoolwork. So decide whether you want to be an A student and start working on it, because there is power inside of you. The infinite power is inside of you, and the time you decide to tap in that power, you will become who you want to become in your schoolwork.
Welcome back to our last push session for physical sciences, paper 1, which is physics. So before we went for our short break, we managed to look into some of the very important things in as far as, your linear momentum and impulse. So over the break, I left this slide, open so that you can try and familiarize yourself with the scenario, right? So we've got a 400-gram ball that is approaching a baseball player horizontally in a western direction. Okay, direction, very, very key. Velocity, momentum, change in momentum, net force, impulse, all of them are vectors. Okay, now it approaches at a speed of 40 meters as indicated. The baseball player exerts a force of 400 newtons on the ball in the eastern direction. Now, when the baseball player hits the ball, he applies a force on the ball. There is a collision between the bat and the ball. During that collision, the bat exerts a force on the ball exerts a force on the ball, according to Newton's third law. Those forces are equal in magnitude but opposite in direction. Now, the first question, once again, is a definition. Define impulse. So impulse is the net force, the product of net force and time acting on an object, as you'd get it as well from the data sheet, right? And then the examiner says, calculate the velocity of the ball immediately after contact with the bat. This is 4 marks, right? Pay attention to that. So what do we know? We know that F net delta T is equals to change in momentum, which is mass V final minus V initial, right? So we will take, for argument's sake, if we take east as positive or west as positive, doesn't matter. So if west, let's say east is positive, right? Meaning east will be negative. That's our direction. Now we are given the net force. The net force exerted by the bat on the ball is east, which is 400 newtons, right? The time is 0.1 seconds, is equals to the mass of the ball, which is 400, which is 0.4. Okay, and then we want the final velocity after contact, after that collision, less the initial velocity. The initial velocity in this case is gonna be minus 40. So it's minus 40. Right? Where is that coming from, guys? This is the catch. The ball is moving westwards. And if we say east is positive, meaning velocity in the western direction will be negative. So from the equation, final minus initial, it will give us VF minus 40, which gives us, if we, just to do our calculations quickly, it's 400 multiplied by 0.1, which gives us 40, right? This is 40 divided by 0.4, okay? Okay, we get 100. Right, is equals to VF plus 40, right? Meaning that our VF is equals to 100 minus 40, which is 60 meters per second. And realize that it says velocity, and then if 60 is positive, it means this is in the eastern direction, which is indeed what exactly happened. The ball moves eastwards. So the catch here was basically in the direction, right? You need to pay careful attention to that. I just wanted to use that so that we get a sense of how vectors are important in as far as change in momentum and impulse, right? Okay, and then work energy and power. That's another headache area, but I genuinely feel that it's possible to get a lot of marks from it, from the definitions and the free body diagrams for starters. Right. Now, the following definitions are very important. Work done by a force. The equation will say W is equals to F delta X cos theta. Right. So, work done by a force is captured in that equation. What is work? When is work done on an object by a force? Then this says to us that what does work on an object is actually a force. So, the product of the force and the displacement. So theta is actually the angle between these two vectors, force and displacement. So if the object pushes if a force pushes an object forward and the force is acting forward, what's common there is that the displacement of the object and the force are in the same direction. Then that object is got cosine of 0 degrees, which is +1. So that cosine of 0 degrees tells us that this force is doing positive work. Right. If, let's say, kinetic friction, which always opposes the motion of the object, an object is pushed forward on a rough surface, meaning the kinetic frictional force is acting backwards. So that force does work, and then the angle between those two forces, those two vectors, is actually 180 degrees. Okay, right? That's -1, meaning that kinetic frictional force is an example of a non-conservative force. We'll get to that. Actually, does negative work on the object. So our special angles, in as far as simple work done by a force, is that if the force does positive work, the angle between the force doing work and the displacement of that particular object, it must be 0 degrees, meaning they act in the same direction. But if they act in opposite direction, the displacement is opposite to the force doing work, then that particular force does negative work. And then also the question of when is no work done on the object. When the force acts perpendicular to the object, let's say the displacement, let's say this is the force, right? This is the object of mass M. It is displaced in that direction. Okay, there's a normal force acting on it. So the angle between the normal force and the displacement is actually 90 degrees. Hence, cos 90 degrees, according to that formula, is equals to 0. Then, therefore, this force does not do any work on the object. Right. So we've spoken about positive, and then the principle of conservation of energy, as we have mentioned it earlier on. In a closed system, the total mechanical energy at point A equals the total mechanical energy of the same object at point B in the same system, right? And then we've also have the work energy theorem. W net is equals to delta EK. What that says to us that the total work, which is the net work done on an object, equals to the object's change in kinetic energy. Right? So this is also what captures the theorem in terms of the definition. And then I've spoken briefly about kinetic friction as a particular example of a non-conservative force. Right? And then a conservative force is the force for which the work done in moving that object between 2 points is independent of the path. So the practical example of that is the force of gravity. This is what you need to know. Force of gravity is our conservative force, and then the kinetic friction is our non-conservative force. Why non-conservative? Because when this force does work on the object, even the mechanical energy of this object does not remain constant. That's what is non-conservative about the kinetic frictional force, right? And then we also talk power in the context of mechanics. P is equals to W over delta T, right? So these are some of the concepts that should come immediately to your mind. All right. Okay, here's a scenario that has got to do with work energy theorem as a practical example, right? A rescue helicopter lifts a man of 75 kg. We're given the mass of the man who is initially at rest. Okay, so initially it's stationary, vertically upwards by means of a light, inextensible, massless cable. Light means massless. So the mass of the cable will not be taken into account. And then while the man is lifted to a height of 12 meters, the average tension in the cable is 3,600 newtons or 3,600 newtons. A constant downward air resistance. Now we are not going to ignore air resistance, right? Is that. And then the first question, 2 marks, as we would have predicted, state or define the work energy theorem in words, right? Nothing special about that. We know that W net is equals to delta EK. The total work done on an object is equal to the change in kinetic energy. Done. That's your 2 marks there. Okay. Now, what is of interest to me now is the free body diagram, right? How many marks? 3 marks. What does that say to us? It says that there are 3 forces acting on this man, okay, while the man is being lifted upwards. So For 3 marks, which forces are there? We are told there's a tension force that's lifting the main upwards. Okay, that's T there. Okay, we've got the weight of the main. This force Fg is exerted by the center of the earth on the main towards the center of the earth. That's why it acts downwards. And then while the main is moving upwards, air resistance or friction opposes motion, meaning that it's acting downwards. So that's our kinetic friction there. Right. So that's the 3 marks. For each one of those, you get 3 marks. Now, definition 2 plus the free body diagram 3, it gives us a total of 5 already. So it means we can really try and get the easy marks. Then beyond that, name a non-conservative force acting on the main, 1 mark. Now, when it says name, you don't explain, you don't define. It's either you know what is a non-conservative force or you don't. And if you don't, I think I'll remind you once again, we'll remind each other, a non-conservative force, an example of a non-conservative force is kinetic friction. It's the force for which the work done on the main is irrespective of, the path taken. It's independent of it's dependent on the path taken. So go back to your examination guideline, read that definition. But in this case, we are not defining a non-conservative force. We are giving a practical example of a non-conservative force, in this case, which is friction or air friction. Okay, and then calculate the work done on the man by the gravitational force while he is being lifted. This is 3 marks. Anyone can get these 3 marks. Now, the work done by the gravitational force, it means work done by Fg is equals to Fg delta y cos theta. Right, let's ask ourselves, the man is moving upwards, is being hoisted upwards, the gravitational force acts downwards. So what type of force, what type of work does this force do? It does negative work, because the angle between the displacement of the man, delta y, because it's vertical, and then here we've got Fg. So the angle between these is exactly 180 degrees. These are angles at a point on a straight line, meaning that this force does negative work on the man, right? So, and remember, Fg is equals to mass times acceleration due to gravity. So in other words, this is going to be mg delta y cos 180 degrees. Guys, the minus must be there because this is negative work, and we know that work is a scalar, yes, but we must know whether the work that's done by this force is actually in the direction of the force or in the opposite direction of the displacement. That's why we need to indicate whether it's positive or not. Right. So that's one practical example that one might consider. And the other thing that we also need to make it very clear is the issue of the work net in terms of the work energy theorem. The work net in itself means total. So there will be different ways in which you can determine the network the network that is done on an object. First, we can determine the change in kinetic energy. And if we talk about the change in kinetic, is kinetic energy final less the initial, right? Or what does work net is the net force. So in other words, we are saying work net equals the work done by F net, because it's work done by a force. And which force are we particularly talking about? Is the net force. Then it's net delta x cos theta. We are fine. And then if we identify forces, like in the example of the man, who was being lifted up, the total work done on the man in this case will be work net is equals to work done by the tension plus work done by gravity, by gravitational force, plus work done by the frictional force, right? So the total of those works, if we may refer to it, gives us the network or the work net, if you wish. Then this is one practical example in which you can use to determine the network. So it will depend on what you are given. If there is a change in velocity, it obviously means you can calculate the change in kinetic energy. Right? So those some of the few examples. And then we've got three energy principles in as far as work, energy, and power. The first one that we covered in grade 10, which is the principle of conservation of mechanical energy. Mechanical energy of a closed system, the total remains constant. Okay, it should be in a closed system. Ignore air friction, ignore the friction of the surface, it doesn't matter. So we are saying that in a closed system, the total mechanical energy of an object remains constant. This is where we were in grade 10, right? Okay, and then quite recently we looked at the work energy theorem. The example that we just used speaks to that. And then the other energy principle, because the examiner will prescribe and say, using energy principles, and then calculate the work done by the non-conservative force. And the non-conservative force in this case is the work done by the kinetic friction, right? Which causes the change in mechanical energy, because some of the energy is used to overcome friction. That's the work done due to friction. But I don't want us to get lost there. Remember, when you see the non-conservative force, it certainly means that that work is done by the frictional force, right? So those are the three energy principles that we ought to remember. All right. Okay, I've briefly touched this in terms of grade 10 and 11 work, right? The quantization of charge principle, which is exactly that. It says that the charge that exists in the universe is an integer multiple of the elementary charge, right? We also managed to look at electric field and electric field at a point. I think we need to distinguish between these two. Electric field, let's say we've got a positive charge, point charge in space. Around that positive charge, what exists? There's an electric field, right? What is missing there? In a field, a unit positive charge experiences a force, right? So if we place a unit positive charge there, in this field created by this big charge, this unit positive charge will experience a repulsive force. That's how the field around a positive charge looks like. So it means the opposite will be true for a negative charge, right? And then when we talk about electric field at a point, we're talking about this. This is electric field at a point, right? What do we mean by that? We are saying this is the force experienced per unit positive charge. Force experienced per unit positive charge. Okay. So the key word positive, very, very important, because that's the unit of charge. So E is equals to F over the unit positive charge. Take note of that, right? And then a practical example, just to remind ourselves, okay, the 2-point charges A and B, they carry a charge of plus 1,2 nanocoulombs and plus 1,5 nanocoulombs, right? Okay, let me go back. All right, they carry those two charges. And remember, 1 millicoulomb is equals to 1 times 10 exponent minus 3 coulombs. 1 microcoulomb is equals to 1 times 10 negative 3 coulombs. 1 nanocoulomb is equals to 1 times 10 negative this is milli negative 3, that's negative 6 there. Then this is nano 9, okay? And then 1 picocoulomb is equals to 1 times 10 negative 12 coulombs. So the examiner does not provide you with these conversions. You need to remember them from the top of your head, right? And then they're placed in a vacuum, means this closed system, and then X is a point, right? X is a point. So there are only two charges, QA and QB, right? Now, state is like defining Coulomb's law in words, right? Go back to your data sheet. F is equals to K, QA, QB over R squared. So the electrostatic force of attraction or repulsion is directly proportional to the product of the charges and inversely proportional to the square of the distance. So the issue of between their centers is not particularly important here, because in their very nature, charges are very small particles that you may not even see, you cannot even see with your naked eye. So it's between the two charges in space. But the mathematical relationship, F is directly proportional to QA to QB over R squared, is what is captured by the Coulomb's law. And then 2 marks guaranteed, right? And then calculate the net electrostatic force experienced by the electron. So an electron is a charge on its own. So in other words, at point X we place an electron which is negative, right? So an electron has an elementary charge E, which is equals to negative 1,6 times 10 exponent negative 19 coulombs, right? So there's interaction between QA and the electron. There's interaction between QB and the electron. In other words, the examiner is saying to us, determine the force, electrostatic force experienced by the electron placed at point X due to QA and QB, right? So the point of takeoff, there is our point X, okay? The electron is negative, and then QA is positive. It means the force exerted by QA on the electron is in that direction. So the electron is attracted towards QA, right? So this is force due to QA, right? And then QB is also positive, and the same electron is still negative. Then QB will attract the electron again. This is not a scale diagram. This is force by QB, right? And then after that, we can apply the Coulomb's law, right? For the force of QA on the electron, and subsequently the force of QB on the electron, and do the net. But what is important is that the force exerted by QB is in the opposite direction to the force exerted by QA. That's where the catch is. So if this is positive direction, this must be negative. So in other words, it's going to be F net is equals to force by QB on the electron less the force by what? QA on the electron. Why? Because the force by QA is in the opposite direction to the force by the QB. Now, it means then you use the Coulomb's law to calculate. So when you do the calculations, do not substitute the type of charge, especially the negative, because it will mess up the vector diagram, which will help us to determine the direction. Very, very important. I think the moment you are able to come up with the vector diagram, the science is done. Then you may do your calculation. So do not rush into the calculations without having a clear understanding of the vectors involved. Right. I hope it makes sense. So this is more like a multi-step problem. That's why it carries a total of 5 marks. Right. Okay. And then the other part that's very, very important is electric field at a point. We know that electric field at a point is E is equals to F over Q, right? And then also when we calculate electric field at a point, it's E is equals to K Q over R squared, all right? That's where it comes from, okay? Now we're told that two charges M and N are on insulated stands. Now the mere fact that they're indicating that this is an insulated stand, it says to us that this is a closed system, okay? It means the net charge during any physical process that may follow from this, the net charge will actually remain constant, right? They are separated by a distance of 0.15 meters, and P is a point. So in this closed system, there are only two charges, M and N. P is not a charge, it is a point in the field of M, and at the same time, it's in the field of charge N. That's our understanding. Now we're told that N carries an excess of 5 times 10 exponent 6 electrons. Now let's ask ourselves, if N carries excess electrons, we need to ask ourselves the very simple question to say, is N carrying a negative or a positive charge, and why? So if electrons are in excess, it means therefore N carries a negative charge. So for us to determine, for argument's sake, the charge that N carries is going to be Qn is equals to N multiplied by E. What is this? Wait a minute. We have discussed this from our grade 10. This is actually the principle of quantization of charge. To say for us to determine the charge on N, we need to know how many electrons are in excess. We multiply that by the elementary charge, which is negative 1,6 times 10 exponent negative 19 coulombs. So the charge of N, for argument's sake, would be 5 times 10 exponent 6 multiplied by negative 1,6 times 10 exponent 19. So whatever that is gives us the charge of N. Okay, you can do it. It's fine. It's not our focus for now. And then maybe the examiner may say, right, now that we know the charge of N and we know the charge of M, P is a point. Now we want to calculate E net at point P due to QM and QN. Right? Now, if we place a unit positive charge, let's say P is our point there. That's our point P, right? We place a unit positive charge. We know that M is positively charged, and the unit positive charge placed at point P is also positive, as its description suggests. It means that the unit positive charge placed at P due to M, it will experience that repulsive force. So this becomes E due to QM, right? And then at the same point P, we place the same unit positive charge, and we know that N is negative. Now the force exerted by the charge N on the unit positive charge placed at P will be in that direction because N is negative. Then therefore this is E due to QN. So our this is QM. Okay, this is Q. Oh, this is QM. Yes. Then that's our E due to QN. Right. So E net is the sum. It's E due to what? QM plus E due to what? Q N, right? But remember, E due to QM is in the opposite direction of E due to QN, meaning that if this is positive direction, and then this must be what? Negative. Therefore, when we do our KQM over R squared, here must be a minus because this other one due to QN is negative. It's in the negative direction. EQN over R squared. Then what follows after that, obviously, is the mathematics. But the science that is important is actually making sure that we understand the vectors that are involved, right? And also, another very, very important thing, when you substitute the charge, do not put the minus for the type of charge because it will mess up our vectors. I hope it makes sense, right? Okay, that's as far as electrostatics, guys. And then electric circuits, another area where still it's very possible to get, the minimum number of knocks that we require and beyond. The following definitions, EMF, very, very key. We know that V is equals to W over Q, right? Now, potential difference between any 2 points is the work done, okay, per unit charge or per coulomb of charge. So when we talk about EMF, we are actually talking about the maximum energy that a battery can supply for every coulomb of charge. Say for argument's sake, we've got a voltage in EMF, let's say of 12 volts. What does that mean? It says to us this battery can supply 12 joules of energy for every coulomb of charge. So in other words, 12 volts equals 12 joules per coulomb, right? So the examiner may say define 12 volts of EMF of 12 volts or define EMF. You must be able to put that in context and make sure that you understand keywords per unit charge, maximum energy or maximum work, because there is a W there, right? And then terminal potential difference, this is what you call your V external, okay? This is what you refer to as your external voltage in a cell. I'll make a practical example of that just to bring that into context. And then quite recently we did an experiment that has to do with internal resistance of a battery, right? So the internal resistance of a battery is actually in series because all the current in the circuit passes through the battery or that internal resistance inside the battery, right? So you need to understand that if the terminal potential difference that we talk of, which is V external, it is the sum of, E is equals to Vx plus V internal, right? So this is your terminal potential difference. This is your what you'd refer to as your lost volts. The sum of those two will give you, therefore, your EMF. This is what we did in grade 11, right, in grade 12. But in grade 11, we also said V is equals to IR, right? That's our Ohm's law, okay? This is still V is equals to IR, in the sense that we are saying that E is equals to I multiplied by R plus R, okay? So that's your voltage there, that's your current, and then that's your resistance, okay? Which is still the same thing. Now we are still saying that this is the internal resistance, yet in grade 11 we chose to ignore that. And in grade 10 we looked at series parallel circuits. That's the most important catch in as far as question 8 is concerned, which is focusing its attention on electric circuits. It's important that you first study the circuit and understand it. Understand that this resistor is in series. What makes us say it's in series? All the current passes through it. There's only that one path. That's why all the current passes through that. Then if we have a series or a parallel combination, we know current is split for the same potential difference. So those are the things that you need to remember. So spend more time analyzing the circuit. Use different colors. Wherever there's a split, you change the color so that you know this is series, this is parallel. Right. Okay. Let's look at the data sheet. Very, very critical. I think I've alluded to most of the the concepts there. The only one that is very important, again from grade 11, is the one of energy. Energy is work, work is energy, okay? Because energy is the capacity to do work. So circuits do work in terms of transforming electrical energy into other forms. So these formulae, they speak to the amount of energy, the time, the current, the power, the resistance. All of them, they speak to the energy in as far as electric circuits are concerned. And all this actually we use most of these three for the different variations of electrical power, right? The product of voltage and current, depending on what you are given, then you can choose which equation to actually use, right? Okay. And then there's a simple scenario here that shows a circuit diagram where the EMF is E. So if we're saying E is equals to 60 volts, then the examiner may say define an EMF of 60 volts. What does it mean for this battery to have an EMF of 60 volts? It simply says to us this battery can supply 60 joules of energy for every 1 coulomb of charge, which means it's 60 joules per coulomb. Okay, that's what it means. So the maximum energy or total energy that this source can supply is actually 60 joules, right? And then furthermore, we have got 3 resistors. The thing is, if we trace this from whichever side, if we trace this from the resistor there, you see that's the same current, but when the current gets there, some of it goes that way and some of it goes that way. It means therefore all the current passes through the resistor small r, which is the battery. All the current passes through the 8 ohm resistor. So those are actually in series. But the moment we reach this branch, a portion of the current goes to 30 and some of it goes to 20 ohms. Therefore, current has been split. Therefore, we can say we've got a parallel combination of resistors there. Right? Now, we've got E of 60. We are told that the voltmeter connected across the 8 ohm resistor reads 21,84 volts. But now, this is the voltage across the 8 ohm resistor. This can assist us to get what? The current that passes through the 8 ohm resistor, because it's about the 8 ohm resistor. So if we go back to the Ohm's law and say, just a moment, okay, and say V is equals to IR, right? Do we have the voltage across the 8 ohm resistor? This is about the 8 ohm, okay? So this is also about the 8 ohm, right? So the voltage across the 8 ohm is 21,84, right? Is equals to the current through the 8 ohm resistor multiplied by its resistance, which is actually 8. Now, Here's a reason why this question is 3 marks. And I firmly believe that each and every one of us can do it. You identify what is given, go to the data sheet, get the correct formula, copy it as it is given, okay? And then thereafter, make the necessary substitutions, calculate and include the correct SI units. Done. Then, in this case, we know that the total current passing through the 8 ohm resistor is equals to, if I quickly go to my calculator, 21,84 divided by 8. Right? This gives us what? 2,73 amperes. 2,73 amperes. Now, this is exactly the current that goes through the battery, because the internal resistance of the battery is in series. That's why we've got plus small r there. Now, that's why this is 3 marks like that. So it's the formula, the correct entire substitution, and the correct answer. Okay, so after the definition, I think anyone can do that. And then the equivalent resistance or in the parallel resistors. Now we need to know what is parallel and what is not, right? So if you look at this circuit, the 20 and the 30 ohms are parallel. So for any two resistors connected in parallel, you are able to say R parallel is equals to product, which is 30 times 20 over 30 plus 20. Okay, then it will give you the effective resistance. In other words, that effective resistance is 30 times 20, okay, divided by 50. Okay. It's 12 ohms. Right. So R parallel is 12 ohms. Okay. So the 3,73 amperes is split between 30 ohms and 20 ohms. And then maybe you might also want to think about between the two resistors in parallel, which one receives more and which one receives less. Remember, for the same potential difference, in other words, V across 20, let's call this V1, okay, and then let's call this V2, right? So we know that V2 is equals to V1. Why? Because this is a parallel combination of resistors. So potential difference is the same. Then the one that has got the least resistance will have the most current. But if you add the current going through 30 ohms and the current going through the 20 ohm resistor, it must give you the total current, which is 2,73 amperes. Right. Those are the basics, the minimum that you need to actually understand. But it goes even further than that. You can have also, because now we know the current we know the what you call the EMF. We know that E is equals to I, right? R plus R. Okay. Now they want us to determine the internal resistance. Okay. Now we know the total current. So if the EMF is 60 and the current is 2,73. Now let's agree. The 8 ohm resistor is in series with the 12 ohm resistor. This is 12 ohms. We've established that. So it means we've got the 8 plus 12, which gives us the 20, plus this unknown internal resistance. And then the rest is history. Okay, so part of the 4 marks there is understanding that R parallel is in series with 8 ohms. Okay, which gives you that 20 ohms, right? Which is exactly that. Okay, so it's important for us to actually understand the circuit. There's a parting shot that you need to know which one is series, which one is parallel. Otherwise, you end up mixing things. But these are actually easy marks that you can actually get. At least you need to attempt. Right. Okay. That's as far as circuits. And then your second last question is most likely to be on electrodynamics, electrical machines, which is your motors as well as generators, right? Now, remember, we've got the Faraday's law of electromagnetic induction. So the principle that underpins or the principle on which generators operate is actually the principle of electromagnetic induction as explained by the Faraday's law, right? So Faraday's law is something that we might have covered partially in grade 11. Very, very important. go back to that. And then the motor effect, where there's a current carrying conductor, around it there's a magnetic field. So if we subject a current carrying conductor to a magnetic field, it experiences a force. That's the turning effect of a force, which has to do with the motors there. And then the energy transformation. Okay, so for generators, we know that it's from mechanical to electrical. For motors, the opposite is true. It's from electrical energy to mechanical energy. And then the rules for determining the direction of, induced current, the direction of the force, the direction of the field. So there are three things. So you need to also familiarize yourself with that. Right. Now, the following table kind of simplifies and gives us a guide in terms of what needs to be done in comparing similarities and differences between a motor and a generator. Okay, so that's with respect to energy transformation. That's with respect to the the components or the structural differences. So make sure that you understand the difference between a motor and a generator. So without any waste of time, if maybe I can quickly zoom into this. You see there are two machines there. There's machine A and machine B. First of all, we have to determine whether the machine is a motor or a generator. So if you look at machine A, with that input, it says we input mechanical energy so that we can get electrical energy. It means this is a generator. But the moment we see these components, this looks like a double C. So this means it's a DC generator. Okay? So the double C that we talk of in this case is your split rings. Okay? It's your split rings. Now, machine B, it is a motor. Why? Because of the power source. Okay? So the source says to us that we input electrical energy. But this is a direct source. So this is a DC what? Motor. Okay? So that's how we distinguish between the two. And basically these are easy marks that each and every one of us can be able to get. Right. Now, classify the above electrical machines into a DC motor and generator. Okay? So we've agreed that this is a generator, but it's DC based on that. While this is a motor, it's DC motor based on that. Right? Because of the energy source. Right? Then the principle name. I think we've encountered this multiple times. When you name, it's either you know or you don't. Okay? So you don't explain anything. The principle is the principle of electromagnetic induction. It is explained by the Faraday's law. So the correct response to that would be electromagnetic induction. Right? We would also accept the Faraday's law because it explains what happens during electromagnetic induction. But if it were a motor, then we will therefore say it's the motor effect. Right? That's basically that. And then last but not least, guys, go back and look at the different graphs in terms of the outputs of your DC current or your AC current. Okay, if you look at the one on the left, let's call this graph X and let's call this graph Y. These are both for generators. Okay, this one changes direction in every half cycle. So this is, in other words, this is an AC output because of the direction of voltage changes every half cycle. And then how many cycles are here? It's only one. It's one complete cycle here because it's up and then down and then back. It's one. And also this one for graph Y, it's a DC. Why? Because the direction of current doesn't change. And this is half a revolution and then another half. This gives us one complete cycle. Right. Having said that, I think we can go on and on, but because of the time constraints that we have, we are forced to say, okay, this is the most that we can do within the time that we have. And I most certainly hope that the legal discussions here and there, we are all over the place, is going to most definitely, contribute in your confidence so that you perform, much better. But beyond this, try and apply some of these tips that we have shared with you and most certainly improve on your performance. For myself, Themba Ncube, I just want to wish you all of the best for your paper and goodbye for now.